I'm Karajo and I'm going to present Lab 4 DC and RC circuits. The purpose of this lab is to do circuit simulation experiments on basis of energy conservation law and current conservation law. Energy conservation law is basically a loop rule, which refers to the sum of the voltage differences across all the circuit elements must be zero. And current conservation law refers to total electric charge in an isolated system never changes. The two equations apply are resistance equals to delta V over I, and for the last RC circuit section, I'm applying the equation delta V equals to delta V0 times e to the negative t over RC. Starting from section 2, at the very beginning, I'm assuming that I1 equals to I2 equals to I, since all the elements in the circuit are serially connected, and we can get a periodic value of I by applying the equations I listed, and basically it means that the voltage of the battery equals to the voltage of the each elements in the circuit, and the voltage of the resistors can be calculated by I times R, and from observation, the reverse of ammeters wouldn't affect the read of data, and replace one of the ammeters with a voltmeter will get the reading that voltage is 3 volts and I is equal to 0 amps. And after making the voltage meter again back to the ammeters, the reading will be 0.02 amperes, which is quite close to the theoretical value I calculated. And the sum of the individual sections of V should be 0 due to the loop rule. This is the voltages for each element I get. For the battery itself, it's 3 volts. And for the resistor part, they also get a value. And the sum of all the sections add up to 0 due to the loop rule. Why no change in current when attached voltmeter? Because the voltmeter has extremely high resistance, so the charge would prefer not to travel through the voltmeter. Instead, it will travel through the resistor, which will cause no change in the circuit, and replace the voltmeter with another ammeter. Since ammeter has extremely low resistance, the current will prefer to travel through the ammeter, so it will skip the second resistor, and it will result in a reading that the ampere increases from 0.02 to 0.06. And the resistance can be calculated by delta V over R, so I calculate the resistance of the resistor by the data I read, and basically they're really close to the theoretical value. And for section 3 RC circuits, so during the charging process of the capacitor, the light of the bulb will dim gradually. It will shine brightly at the first place, and when I first connected the battery to the capacitor, the reading of the current in the circuit will increase sharply and goes down slowly. And it is exactly the same observation for the discharging process. These are the values I get for the time it takes to charge and discharge the capacitor for both when the light bulb is 10 ohms or the light bulb is 20 ohms. Basically, it takes a little bit longer time to discharge than charge, and the higher the resistance of the bulb, the more time is required to do the discharge and charge process. For section 3.1, on the left side, it's my raw data for the time starting from 0 second to 20 second. And I did a little bit of manipulation of the data, and this is what I get, a diagram of line delta V over delta V0 versus time, and we can tell that it's in a linear shape. And why do we need to calculate this? That is because due to the equation the instruction gave us, we can evolve it into line delta V over delta V0 is equal to t times the time constant, which is negative 1 over RC. So basically, after we get in this diagram, t is the x value, line delta V over delta V0 is the y value, so the time constant is just the slope itself. And according to my data, it would be RC would be 5.905. According to my data, RC is 5.914. The theoretic value should be 30 ohms times 0.2, which is 6. So I think my results are pretty close to the theoretical value. Some further discussions. So if I'm doing this lab in real life, I'm using actual ammeters, what will happen? So an actual ammeter has a really small amount of resistance. It's not zero or ideal as we did it in simulator. So the data would be a little off, but it wouldn't affect much. And if I'm using a real battery to charge a real capacitor, and if there's no resistor in the circuit, of course, if there's no resistor in the circuit, the charging process would be much quicker. But also there is wire in real life, and the wire has more amount of resistance as well. So it will still be quicker, but not as quick as if we don't remove the resistor in the simulation part. A simple conclusion. So from this lab, we visualize the concepts of energy conservation law and current conservation law in circuit by doing circuit simulation, and we also understand the properties of DC and RC circuits.